In this video, we will solve principal stress problems. First problem, we have a solid rod, diameter is 20 millimeter, and a section is given, and in this section, point A is found critical, and we have to determine the principal stress and the maximum in-plane shear stress in this point. First we have to do is we have to cut. When we cut and take the left side, we have such a free body diagram, and the external load here is 400 Newton, and possible internal loadings are a normal force. There is no shear force because the external forces do not have any vertical component, and we may have a bending moment around the centroid of this section. Now we write the equilibriums. The first one is sigma fx equals to 0. Here we have two forces, the normal force and that 400, normal minus 400. Well, we determine N as 400 Newton. And if we write the equation sigma Fc around the centroid of this section, around this point, then we have to write down the moments. And these are, well, around C. Well, this has an anti-clockwise, that means positive moment, 400 times 0.25, and this moment is negative, and as a result, the internal loadings are a normal force and a bending moment. Now, before making the calculation, stress calculation, I need to determine the cross-section of the critical section and the moment of inertia for bending. Now the stresses. We know that the normal force and the bending moment will create normal stresses, and we can add them by superposition. So let's try to do it. The normal stress is a tensile positive divided by the area. And for M, if you have a bending moment in this direction, so your section is here and your point A is here, you bend like this, and over here you will have a negative normal stress. That means minus 100 is my bending moment, 0.01 is the, you see this is my neutral axis, and point A is over here. This distance is 10 millimeter, and that is my moment of inertia. So we put the numerical values, and as a result, we find that due to the normal force and the bending moment, the normal stress is minus 126, a compressive stress. Next, about the shear stresses. Shear stresses develop due to shear forces and torques. So we have no shear and no torsion, so no shear stresses. As you see, as a result, you can show the stress state in point A with a simple volume element. There is only a compression 126. If you write down the stress state, sigma x is minus 126, sigma y, that's this direction, is 0, tau xy is also 0. we have to determine the principal stresses. This one is a principal stress. Why? Because on this plane there is no shear stress, and principal planes are planes with no shear stresses. So my first principal stress is this one. That one is this one. But we also know that there is a third axis which is perpendicular to the screen, that is sigma z, and that is also 0. So we have 0, 0, minus 126. Well, this is the smallest one because it has a negative sign. That is sigma 3, and these two are sigma 1 and sigma 2. For the maximum shear stress, we have such a formula. When you know sigma x, sigma y, and tau xy in plane stress condition, you can calculate this with this formula as 63.0 megapascals. And the orientation of these maximum shear stress points, you can calculate the tangent to theta, which is infinite, and your theta is 45 and minus 45 degrees. So you can solve this problem also with the help of a Mohr circle. So you know these values. So for this surface, well, let's call it surface A. Well, your sigma is minus 126, your tau is 0, so your point is somewhere here, minus 126. And for this surface, let's call it surface B, you have the coordinates 0, 0, that's sigma and tau, and that is this point. This is point B, and this is point A, and you can draw the Mohr circle like this. Okay, well, this goes through the origin, and as you see, your sigma 3, and that is your sigma 2, and sigma 1 is also 0, and you can determine also the maximum tau max as the radius, which is the 126 divided by 2. This length divided by 2 is the radius, and as you see, it's 63. And the angles from the reference point, from this point to the maximum shear stress and mean shear stress is 90 degrees. So 90 degrees is 2 theta, and theta is 45, as we have found with the help of a formula. You see, you can use the formulas to determine principal stresses and maximum shear stresses, and you can also use the Morse circle. We also know that on the maximum shear stress planes, the normal stress is the average normal stress. As you see, sigma is equal to sigma x plus sigma y over 2 at minus 63. Or if you draw the volume element for the maximum shear stress planes, these are in 45 degrees, and the acting normal stresses are minus 63, and the value of the sigma tau max is 63, and on the other plane it is minus 63. Another problem, we have a solid shaft is subjected to a torque. Where is the torque? This is the torque. Bending moment, this is my bending moment, and the shear force, and the shear force. Determine the principal stresses in point A. Here we have a section, and here is my point A. First thing, well, we can calculate the section properties, the moment of inertia, polar moment of inertia, the Q value for the shear. but we will come to these values later when we use them. So let's cut through our critical section. This is my section, and in this section, the axes are X, Y, and Z. Possible internal loadings are: there may be a normal force, a shear force, bending moment, and a torque. So and these are the acting external loads. Well, we have to use the equilibrium diagrams in order to determine these internal loadings. Well, let's start with sigma Fy equal to 0. Well, sigma Fy is this direction. Here we have only the normal force N, but well, since there is no external forces in this direction, N equals to 0. Then we can take the sigma Fz equal to 0. Here we have Vz, that's this force, minus 800, minus 800, and that gives me V equal to 0, Vz equals to 800 newtons. So we already have the two forces, and we have calculated this one, and we have determined these two one by one. Next, come to the moment around Y. That's a moment around the longitudinal axis of the rod. It's a torsion. So take your right hand, place your thumb in the positive direction, and your fingers will show the positive torque. So let's write down sigma m y equal to 0. Here we have minus 45 Newton meter, okay, and we have plus tau y equal to 0, ty, which is the torque, is 45 Newton meter. Now we have also calculated this value. We know these two values, this one and this one. The only thing which remains is the bending moment. Let's clear everything. Well, the bending is around the axis X. So the positive direction is this direction. Here we have sigma mx equals to. Well, as you see, we have an acting bending moment that is 300 Newton meter. That is in the negative direction. Then we have the bending effect of this 800. So this 800, well, tries to rotate this section in the positive direction, and the bending moment arm is 450 millimeters. That is 800 times 0.45. The direction is positive, and then we have the moment m. Here m is in the negative direction, so let's put the negative sign in here, equals to 0. So well this one gives 360, and the result of this equation is mx equals to 60 Newton meters. Well, we can do calculation. These two give minus 60, and mx is also minus 60, and its direction is as shown over here in this direction. Now we know the internal loadings: torque a bending moment, and a shear force. Let's start calculate the stresses in point A. So if you take the shear force, and which is acting in this direction, that's 800 newtons. So the stress distribution of the tau is like this. It is maximum on the neutral axis, and on the surfaces the value is 0. And my point A is on the surface. Point A is on the surface, so we do not have any shear stresses. Bending moment first. Well, we have a bending moment as you see over here. It's acting like this, and so if a bending moment in this section is trying, means it tries to bend the bar like this. In the point A, we will have a positive tensile stress, and you can calculate this stress by, this is my moment in Newton meters, that is this distance, okay, it's 25, and that is the moment of inertia which I have calculated. So as a result, we have 4.889 megapascal. There is no normal force, so no normal stresses due to bending force, due to normal force. We have torsion. Well, we all know when we have torsion and it is applied, all surface points will have the maximum tau max value, like my point A. You do the calculation by taking the torque Newton meters, that's in meters, and you do the calculation for J, which is the polar moment of inertia in meter to the 4, and the tau value in point A is 1.833 megapascals. Okay. Well, here you have the volume element showing the stress state in point A. You have a positive tensile normal stress X in this direction, that is sigma Y, and we have a shear stress with a value of 1.833. So my torque in this bar is headed so that we have a torque in this direction, which is in the negative direction. So we show our tau xy like this, and this is the stress state for these coordinates. If you want to calculate the principal stresses, you can use the formula sigma x, sigma y, and tau xy, put the numerical values, and in the plane, your principal stresses are 5.5 and minus 0.611. So these are in the plane of this section. We have another stresses which is perpendicular to the plane, which is 0. So if you want to name the principal stresses with subscripts, this is the maximum, this is the minimum, and this one is sigma. Well, here you have your sigma 1, sigma 2, sigma 3 principal stresses. In this video, we solved two principal stress problems. You know that such problems can also be solved with the help of a more circle, and for more circle solutions, we have a special video. Thank you for listening.